Hi everyone, welcome back. And today we'll be doing this question called find minimum in rotated sorted array. This is a medium rated question as part of our series, and let's just jump straight into it. So suppose you have an array of length n that is sorted in ascending order, and it's rotated between 1 and n times, which is the length. So an array like this, if rotated 4 times, becomes like this, and if you rotate 7 times, it just goes back to its original because there's 7 items inside. So the number of times that it was rotated is not known to us, and it honestly doesn't matter as well. But what matters is that this is originally a sorted array, and you rotated it as such. Um, and so you can just visualize this as like a chain sort of thing. So yeah, given the sorted rotated array, of unique elements, we need to return the minimum element of this array. And you must write an algo that runs in O log n time. So this is where the challenge comes. Like if it was just a straight up, like if we really wanted to save time, all we could do is just do something like this, like return min nums. And this will actually work for the smaller test cases. But the thing is, the min operation takes n time complexity because it will traverse through every single item inside the array and identify one. Another slightly faster method would be we sort this entire thing and get the first item. That will also work, but it might be a little slow because sort operation in Python takes n log n. So n times log n. And any large value that we put inside it will just it'll just be not right. It'll fail in when we submit for the other larger test cases. So the hint here is log n. And one of the patterns that we can recognize is that whenever they have given us this kind of hints, it is mainly asking us to do some sort of binary search. So what is binary search? It typically works with a sorted list. It works with a sorted list, and it needs something like the main trick of a binary search is that at each step it cuts the problem. Uh, each step it trims the problem by half. It trims the search space by half at each point. So let's just quickly, I will do a quick visualization on what binary search is and how it looks like. And then we will go to how we will implement this in LeetCode. So let's say we have an array like this, like a sorted array like this. And if we want to find, let's say, the number 2, we want to find the index in which where number 2 is. What you'll do is you'll have a left pointer and a right pointer and a middle pointer. So left is this, right is this, and middle is this. So in a sorted array, if I ask you the number 2, will it be in this zone of things or will it be in this zone of things? You'll narrow down and say it'll be somewhere in the middle over here. It'll be in this zone. So then you trim the right pointer to come to this middle section, and now your search space is reduced to just this. Oops. Your search space is reduced just to these 4 items. And likewise, you just keep going until you see the value itself, until you see the number 2 that we're searching for. And that is what a binary search is. It works on a sorted list, and at each step, it trims the problem by half. By doing so, we have a logarithmic search space efficiency improvements. From like maybe 10,000, it becomes 5,000, 5,000 becomes 2,500, and 1,200. So it dramatically reduces the search space, and as a result of that, it doesn't explode, and it'll be one of the most efficient ways to solve this question. So now the problem comes in. In a sorted array, it works, yes, but how about in a chained sorted, like in a rotated array? How does this work? All we need to do is we need to figure out the different scenarios. So I wrote down the different scenarios that we can anticipate, and I just put it over here. Let me just copy paste it. So it'll look something like this. I'll just uncomment this so it looks nicer. So in effect, if we have an array like this, and we have a left pointer and a right pointer, and we will get a middle pointer somewhere here, there are a few different scenarios that we can run into. We need to basically return the minimum element of this array. If it was just a clean sorted array, we don't even think so much. We can just return this. So what is the logic that we can use over here? If the leftmost item and the rightmost item, when we take these two, if the left is smaller than the right, if this is smaller than this, we can just return the left. We don't even need to think so much because if it was rotated, the biggest element would move here and the smallest element would be in the next position, would be somewhere here, or and so on and so forth. So in a rotated list, if for somehow we have the left index item is smaller than the right index item, we know that the sequence is ended, and hence we can just return the left. Now let's think of the next scenario, which is the next two scenarios are something to do with the middle element. So right now this is a rotated array, and the minimum most item is 1, and the middle item is this. So in this scenario, 6, and the middle is 2, and the right is 5. The middle is smaller than left. So that way we know that the smallest item is somewhere in this zone. It's just that, like, there's no way that the smallest item will be over here, right? Because the big item is over here, and the medium item is over here. So it's possible that the medium item itself could be the smallest item, but the logic is it will not be in this zone anymore, because anything to the right of the middle item should be bigger than the middle item, and anything to the left of it is likely to be smaller, or it will be part of this series of things. So that way we know that the binary search should be to the left now. And likewise, if we flip the script to the other side, whereby we have a medium item over here, so 6 is left, medium is 8, and right is 5. If we know that the medium is bigger than bigger than the left, if we know that this is bigger than this, we know that the smallest item is probably not going to be in this zone. Like, it's more likely that the medium item, the smallest item, will be in this zone of things. So this is the series of checks that we need to do. First thing is we need to check if this and this matches. Like, if this item is smaller than this item, we just return this item. We don't need to think so much. In this scenario, this item is not bigger than this. This item is bigger than this, and hence we know that it is a rotated array, and hence we need to find some way of binary searching through reducing the search space to get the item that we want. So that's what we'll be doing now. What we'll be doing is we'll be implementing this logic in our code, and I'll try to explain this again as we code it out, and hopefully that makes it clearer for everyone as well. So this is how I like to usually implement a binary search, which is I have a left and right pointer, which is just len nums -1. Maybe I'll reduce the spaces so that it's easier to read. So this is the leftmost pointer, and this is the rightmost pointer, which is length of the nums -1. And I'll create a while loop such that I'll basically be checking that the difference between the right and the left index is greater than 1. If it is greater than 1, we continue. If it's lesser than 1, that means they're right next to each other. We can exit the while loop, and we don't need to keep doing the binary search elements. Next, we need to find the middle element, and the middle element is like this. We don't want to float, so we just round it down to the nearest whole number. And I like to call this lightem and rightem and mightem. And the logic is this is the left item, this is the right item, and this is the middle item. So nums L, I'll just copy paste this, copy paste this, copy paste this, right item and middle item. Now, if lightem is smaller than rightem, which is the first scenario that we mentioned, we just return lightem. And okay, spelling. We don't need to use elif, but I'll just use, because if we return it it's effectively starting new again. So, but it doesn't matter. I'll just use elif in this position. Next, I'm checking this condition, which is the medium item smaller than or bigger than the leftmost item? So elif mitem is smaller than litem. Mitem, m item is smaller than left item. In that scenario, we know that the search space needs to be reduced to this zone. That means we need to bring our right pointer to the medium. So right pointer will become the medium index, the middle index. And another last one, which is if mitem is greater than litem, left will become the medium, which is this. If the middle item is bigger than the left item, we know that the search space needs to be somewhere here, like past. So we will bring the left index to the middle. So left will become the middle. And with that, we can just return the minimum of nums left and right. Nums right. Why do we do this instead of just the left or the right? Because it's firstly, this doesn't consume so much time complexity. It's just comparing between two items. And next, there's a possibility that when we round the values, the middle could be in either, like if it's an even or odd situation, it could not fit nicely. And since it's a low cost operation, we'll just attempt it this way. And by doing so, we effectively get a pretty efficient algorithm to get there. Okay, some syntax issues. I'll just comment these out because it's giving me issues. So yeah, this passes the test cases. I'll just quickly run through the logic of what's happening again. We have a left index and a right index, starting to the left pointer, rightmost index. And we are traversing through such that the difference between the right and the left should be more than one. When will it be lesser than one or equal to one? It's when they're right next to each other. So until they come right next to each other, we will keep going on and on. And what we will do in each step is we will figure out a middle pointer, and the middle pointer will be left plus right divided by 2. And we'll find the actual values of the different items. And what we'll do is we'll logically compare them, which is if the leftmost item is smaller than the rightmost item, we can assure and guarantee, we have an assurance that this has not been rotated. And if it has not been rotated, we can just say this is the smallest item, and we'll just put litem. Next, if it is rotated, then the whole game switches to the middle section. So the middle item should be lesser than the left item. If the middle item is lesser than the left item, we know that the search spaces should be narrowed down to this side. And to reduce the search space to that side, we do R is equal to middle. And the flip is also true. If the middle item is larger than the left item, we know that the smallest item is definitely not on the left side, but on the right side. So yeah, feel free to just rewind, go back and forth to hear the explanation again if it's not clear, or let me know in the comments as well. But basically, if we run this program right now, this should pass all the test cases because this is one of the more efficient ways to solve this problem. And in terms of time complexity, we can see that this is actually log n time complexity because at each point, we are trimming the whole search space by half. Every time we go through the while loop, we will trim it by half again and again and again. And as a result of that, we have a really efficient way of solving this. And this can only be done if we have a sorted list or some sort of sorted logic in the list. And at each step, we trim the problem by half. And after doing all that, we just return this and we get a final answer. And as you can see, it does a pretty decent job in the runtime. Actually, this is a bit peculiar. Look, why is it 0 milliseconds? But anyways, in terms of time complexity, theoretically, this is a pretty efficient algorithm. And let me know what you guys think. And if you needed any extra explanations for any sections, I'll be happy to explain it more. And yeah, I will see you guys in the next video. Cheers. Bye.